That is easy.
Remember. You know what is that? Basically, it's really cool.
Really?
Yeah.
Wow. But it's going to be like
Well, then leaving is going to be like Mexico. Yeah, you're going to be there like this. Yeah, it's like Mexico.
we were waiting for a long time for this.
The main things are
He did it till yesterday.
Because he was doing like 20
Very far.
He was 22.
Anthony Joshua.
His score is 49. One is against me.
Wait.
About 0.
Each was
Waiting for this game for a long time. 3 or 4 years.
No, that was his
Didn't
part.
want to sign up.
How old is your fighter?
How
How old?
Fresh now.
He was very young, like 3 years old.
But now he's very young.
endorsement.
It's going to be very easy.
YouTube videos.
Advertising and stuff like I've retired.
I would retire for myself.
20,000 pounds a day. That's still like 3,000 a year. That's you tell me you can't live off a grand. Without £1,000 to do something.
Because of money.
I'm sure he has other passions where you don't have to risk
Just chill.
get me to Philippines, grand a week. Grand a day, sorry.
I need to start training.
How old is he?
Did a weight classes. Josh gets killed.
Joshua, the killing is on weather.
The weather's like, it takes what units to bury. It's not
Who against who?
no, I'm asking.
He's amazing. For his weight, he's the best ever. 5 minutes.
Going against the heavyweight was 6 for 6. 100 kilograms. Yeah, he's got good gel. Just one punch, he'll be down.
I would love to see that game 2 years ago.
It would not even matter. Even if Miller was blocking, he would just punch through it. Punch through it, just you shoot.
Through the glass, you mean, yeah?
Quite literally, yeah, through the ring. Which means the wins.
How old is he,
Joshua's tall. Yeah, Johnson's like this.
I would love to see the way that challenge.
Yeah.
Or Joshua should challenge
It
me.
was good fight. Purely on just fight, just power.
Right, so good morning. Good morning. Today we're going to finish revising distillation columns. Especially we'll go through a procedure to calculate the number of plates, which will indirectly determine the height, but in terms of design, the only thing that we will see on this module is how to determine the number of plates of a distillation column. We won't go into details of the width of the determining the width of the distillation column and the height. And why we're going to concentrate on plates, because this is the most important part of the distillation column. If you remember, we said that a plate simulated the fact that we had, instead of that 2 unit operations, a heat exchanger plus a separation vessel. So in each plate there's going to be mass transfer between the liquid and the vapor fractions that are in the distillation columns, and through that mass and heat transfer we will have a change in temperature in the vapor phase and the liquid phase, and change of the fractions as well of the vapor and the liquid. Okay, so here is the overall diagram of how a distillation column looks. So if you remember, last Friday we mentioned that 2 key important things that are part of a distillation column is the reboiler and the condenser. However, not all of the distillation columns will contain a condenser, such as the one from the assignment. Another thing as well are the number of plates and the reflux ratio. Okay? So we will see that later on when we look at the design, but the reflux ratio will determine how much of this liquid that is taken out after the condenser is coming back to the distillation column. And basically the design of a distillation column will finally be decided on playing with the reflux ratio and the number of plates. The higher the reflux ratio, the less number of plates that you need to obtain a separation. The lower the reflux ratio, You need more number of plates. If we need a higher number of plates, then what would that mean in terms of the height of the column? Will it increase or decrease? Increase. So we will see that later on, but perhaps you can start thinking about it. If we have a higher reflux ratio, how would it affect the operation of the column? Increased quantity of liquid going down. So in terms of utilities, so will that increase the amount of utilities of energy that you need, or it will increase it? Increase it, okay? So a higher reflux ratio will increase the amount of utilities that you need because you will have more liquid going to the reboiler. So therefore you'll have more heat needed in order to heat up that liquid. However, you need less plates, okay? So if we have a lower reflux ratio, the capital cost of the distillation column will be higher because you'll need to buy a distillation column that is very lengthy and has a number of plates, and therefore you'll pay a lot for that distillation column. However, the utilities cost that you have, because you have allowed for more plates, the utility cost will be lower, right? And then the opposite, vice versa as well. If you have a higher reflux ratio, the capital cost of the distillation column will be lower. However, you'll need to take into account that the utilities that you will need, that you will pay in order to conduct the separation will be a little bit higher. And there will be an optimum value that we will see how to get it. And here, well, there's a diagram in which we intend to show, can you see that there are some gaps on the plate? So through the gaps of the plate is where the vapor goes up, and then the liquid goes down. And during this, while the vapor is going up and the liquid down on the plate, that's the contact place, and that's where we have the heat and mass transfer occurring in the distillation column. So we said that there are different types of distillation column. If you remember on Friday in HYSYS, they have at least 6 icons for distillation columns. So depending on what we want to achieve is the type of distillation column that we're going to use. So the stripping column, which is the one that basically was the one selected for the assignment, will basically be used for volatile when we want to remove volatile components from a liquid. Okay, so the liquid flows down the column, and then the vapor flows up the column, and whilst it's going through that phase, the volatile components in the liquid will go to the gas phase, and therefore we'll be able to strip them. Okay, so in some cases we may have stripping columns where we don't have a reboiler or a condenser, that we just allow contact between the vapor and the liquid phase, depending a lot on the feed that we have. So we may have a feed which is a mixture of 2 compounds, and as well as we may have 2 feeds as well of the vapor and of the liquid. Now, another type of distillation column is the one where we have a condenser, but we don't have a reboiler. And this is called an absorber column. Okay? So here is, normally in these types of columns we have the opposite. Volatile components are absorbed from the feed gas as it flows up the column, and the liquid flows down the column. So here you can see the feed is at the bottom, and this will normally be in gas and vapor, and then the gas will go up, and then we will condense the gas and reflux the liquid down. Okay, so in these columns we can show that we have a gas and a liquid product going out of it. Now, overall, the design of a separation column. So what does a distillation column mean? So basically it's essentially a tube where we allow a gas-liquid contact. Okay, so it's a tube with a number of plates to allow gas-liquid contact, and therefore, by doing that, we allow mass transfer and heat transfer between the two streams. Normally, the diameter of the tube is determined using fluid flow characteristics. So here is going a little bit into the hydrodynamics of the distillation column, and we will not go into that detail. There's something very important as well to consider, which is the maximum gas liquid flow rate, and that will determine the diameter of the plate column. So what does that mean? Well, we need to use a flow rate that is high enough so that the gas basically goes up and disseminates through the liquid. However, the liquid must be in contact with the gas a reasonable time period that it allows the sufficient mass and heat transfer that we want. And that will basically determine the length of the plate by itself. So the diameter of the plate column will be determined by basically playing with the gas and liquid flow, trying to optimize the mass and heat transfer. Okay, so we change the gas and liquid flow to optimize the mass and heat transfer, and this gas and liquid flow rate that we selected will also indirectly tell us what is the plate column, the diameter of the plate that we need. So you can imagine, if we have a lower gas flow rate or liquid flow rate, will the diameter of the plate be higher or lower? For a low flow rate, do you think that the plate will have a higher diameter or a lower diameter? A higher diameter, okay? So we need to play with it so that we have an enough flow rate to allow enough mass and heat transfer, and also an optimum diameter of the column. If it's too low, not only the diameter of the plate ends the column will be higher, but also you may have problems in terms of pushing up the gas through the column. The length of the column is determined by the number of stages. So again, this is the number of plates that we will have in the column, and that will determine how high the column needs to be. So the separation between one plate and another plate depends as well on the type of mixture that we want to separate. So if we have very dirty mixtures, that means that a dirty mixture is where we have a very small boiling range. Do you remember the boiling range? And then that we have a lot of components in the mixture. Then the separation between one plate to another can be up to 1.2 meters. Okay? Now, for clean mixture, let's say for the assignment example, where we have ethane, propane, just a binary mixture, we can have a separation of around 0.7 meters, so almost half the space that is needed. So that will also affect the height as well of the column, okay? The type of mixture that we have and the separation that we need to allow between one plate and the other. So this is something that I already told you about. The capital cost of the column is primarily determined by the height of the column, and the operating cost is basically determined by the amount of heating and cooling required in the reboiler and condenser. Okay? So this is the parameter that controls both of these costs, are called reflux ratio. So that's the reflux ratio that we saw on the condenser. That's the reflux ratio, okay? So the reflux ratio is a parameter that we can easily change in order to fit the column to the right height and operational cost. So here we have a graph that normally is obtained by industry, where we have on the x-axis the reflux ratio and on the y-axis the cost. And those can be the operating costs or the capital costs. Capital costs are also used called fixed costs. So fixed costs are essentially the purchase of the equipment. Okay? So we said that as we increase the reflux ratio, we need less number of plates, therefore the cost of the unit, the height will be lower and the cost of the unit will decrease. Okay? So those are the fixed costs. However, as we increase the reflux ratio, we need to return more liquid into the distillation column, and therefore we will need more energy in the reboiler and condenser and we will have a higher flow in that. And that will increase the operating cost. Okay? So as we change the reflux ratio, we will have changes in the fixed cost and on the operating cost. So essentially, we want to operate at an optimum cost, which will be the point where the two cross over. And that will be where we will decide to operate the distillation column. Okay? And the distillation column that we will select. So therefore, for this distillation column, we will use, let's say this is just in the middle point, a reflux ratio that is in the middle. And that will give us essentially an optimum number of plates and a reflux ratio which will allow the lower operating cost as well. So let's have a look at an example. In order to now go into the design of the distillation column, okay? So the only thing that we are going to basically calculate to design the distillation column is the number of plates. And why? Because if you remember last Friday when we were in HYSYS, we normally need to input in HYSYS the number of plates. Okay, so we need to, sometimes it's a parameter that is useful to estimate for simulation. So therefore that's why we're going to concentrate on that, but not on the other characteristics that will require a lot of time to discuss and even a whole module. So we're going to use the McCabe field model, okay, which is a type of model that is used in order to estimate the number of plates. There are different types of models, but that's one of the simplest models used for binary mixtures, and that's what we are going to learn today. So this model will be based in a plot of the mole fraction in the vapor and liquid equilibrium. So if you remember last Friday, I said that one of the assumptions, for example, when we designed compressors, okay? So what was the assumption that we made for designing compressors? Isotropic compression, okay? So that facilitates our calculations. Here in separation for distillation columns, the assumption that is made is that in each plate, the liquid and vapor are in equilibrium, okay? So this model will basically be based on a plot of the mole fraction of the vapor and liquid at equilibrium. So we will need to construct a plot where we show the vapor and liquid fractions at equilibrium conditions. So this is the same assumption. The key assumption in the model is that the liquid and vapor flow rates in the column are constant throughout its entire length. That's another assumption. So if the flow rates are constant, obviously you could say, well, the flow rates are going to change because as the liquid goes through the plate, there's friction occurring, loss of energy, therefore the velocity might change, affecting the flow rate. But we're not going to take that to go into too much detail in here. We are going to assume that the flow rates remain constant throughout the length of the column at the inlets and outlets. So the basis of this assumption is as follows. On any stage in the column, the least volatile component is condensing from the vapor and evaporating the most volatile components. If the heat of vaporization of both components are the same, then the vapor and liquids flows will remain constant. And, well, this McAfee model is considered a good approximation for hydrocarbon systems. Okay? So those are the assumptions that the model is based on. So now you will see how we're going to do this approximation using this type of model. Okay, so right now you may have to right now look at the methodology that we're going to follow. Okay, so just check the methodology, and once you get the methodology, basically that's how it is applied to any other case. So we are going to look in this case the benzene toluene mixture, which is at atmospheric pressure. And this is very similar to the case that you have for your assignment, where you have two compounds as well. So here what we have is the TXY diagram of this mixture, where we have the mole fraction of benzene at different temperatures. So again, here we have the liquid vapor equilibrium curve, and then we'll have the vapor phase on this side, the liquid phase on the other side, and then we look at, let's say, if we had a composition of the mole fraction of benzene being 0.3, at equilibrium the liquid will be 0.3 of benzene and the vapor will be 0.5 of benzene at which temperature? 98? Around 98 degrees Celsius. Okay, so at 98 degrees Celsius, 0.3 moles of benzene in the liquid phase are in equilibrium with 0.5 moles of benzene in the vapor phase. Okay, let's have a look at if we decrease the temperature to 88 degrees Celsius. Then if we decrease the temperature, we have a higher fraction of benzene in the liquid, which is 0.62, 63. And then on the vapor phase, 0.81. 81, no? 0.81. Okay, so if we decrease the temperature of the benzene toluene mixture, we will have a higher fraction of benzene in the liquid. Does that make sense? Yes, right? So if we take this mole fraction of the liquid and vapor fraction and mole fraction of the vapor of benzene, we can go and plot it in a diagram. Okay, so in this diagram we have the YX diagram, and basically this diagram, what we show it are the mole fractions. So we have the mole fraction of benzene in the liquid and the mole fraction of benzene in the vapor. Okay, so here we have temperature against mole fraction, and then we have the liquid and vapor in each one of the lines. Here we're basically plotting this liquid and this vapor in the y-axis. So the vapor is in the y-axis and the liquid is on the x-axis. Okay? So how did we get this data point? We basically took it from the equilibrium curves, and we took this 0.3, 0.51. So 0.3, 0.51. And that's what data point. Okay? And then the other one is at 0.6 of the liquid, we have 0.8 of the vapor. And we get this data point. Okay? So we have drawn this curve only with 2 data points, but if we were taking more data points at different temperatures, then we can derive this whole curve that is here. Okay? And what does that is telling us? Well, this is telling us at different mole fractions, at different fractions of liquid, how much you will have of vapor, basically, at equilibrium. Okay, so all of those are at equilibrium conditions. We can see that the curve is going towards the vapor. So the curve is going up on this side of the chart. If it was going down on this side of the chart, that will mean that this mixture will tend to be on the liquid phase. But this mixture tends to be on the vapor phase. Why? Because the curve is going towards this side of the plot. Okay, so we get the XY diagram for base-10 toluene. Let's have a look at the example. So the example, we have a distillation column with a reboiler, okay? And in the distillation column, we have the feed. So 200 moles per second, which is the flow rate of a liquid feed containing 40% benzene, 60% toluene, is to be stripped to give a toluene containing 2% mole benzene as a bottom product. Okay? So here we have the bottom product B, which is 2% mole benzene. Will that be liquid or vapor at the bottom? Liquid. Okay, so we're taking out from the reboiler, but in your assignment, you're taking up from the top of the reboiler, okay, the vapor. But in this case, we're taking from the bottom of the reboiler, so therefore we're taking up the liquid fraction, okay? So we have the bottom product that has to be 2% benzene, and the top product D, 56% mole benzene. So the vapor leaving the reboiler is in equilibrium with the liquid in the reboiler. As equilibrium condition is 6, we can read the temperature for the TXY diagram too. Okay? So this liquid at 2% is in equilibrium with the vapor. So can we get the percentage of benzene in the vapor? Yes, from the chart. Okay? So if we go to the chart, to the TXY diagram, we have 2% of benzene, which is 0.02 here. So here, first of all, we can already know what temperature the reboiler we have, which is 110 degrees Celsius. And then the fraction of the liquid, the fraction of benzene in the liquid, the mole fraction. So that will be 4% benzene. So if the liquid is 2% in here, benzene, the vapor in the reboiler will be, how much did we say? 4%. So vapor leaving the reboiler, what will be in here? 4, okay? So 4% mole of benzene will leave the reboiler, right? Now, we also have the feed. The feed is 40% mole benzene. Okay, so this is the feed. In here, mole fraction of benzene, 40% mole of benzene. We can see that the feed is at 95.5 degrees Celsius. That will be the temperature of the feed. And therefore, if we go and also check a straight line in here, we can see how much it will be in the, but this is fed as, okay. Okay, so this will be the percentage of mole fraction of benzene coming in. So let's have a look in here. So we can do the mass balance of the column. So the feed F will be equal to the bottom product plus the top product, okay? The top product is called the distillate and the bottom product bottoms. So feed equals distillate plus bottoms, right? So we know that the feed is 200 moles per second. So 200 moles per second equals D plus B. If we do the mass balance specifically for the benzene, since we have a mixture of toluene benzene, we need to multiply by the mole fraction of the benzene. So we multiply the flow rate, 200 moles per second, by the mole fraction of the benzene. And then we have the mole fractions of the benzene at the top and the mole fraction at the bottom. 0.56 at the top, 0.02 at the bottom. So we end up with this equation, right? 80 equals 0.56 distillate plus 0.02 bottoms. Now, in order to solve this equation, we will need to give a flow rate, the flow rate that we want to obtain either in the bottom or either in the top. Okay? So let's say if we specify a flow rate in the top, in the distillate of 140.7 moles per second, then we just simply substitute this value and we get the bottom that we need. Okay, so once we have this equation, we can basically determine different values for the distillate and obtain the bottom flow that we will obtain for the different values. So we have now used this value in order to estimate the number of plates. So imagine that you want this flow rate, and now you need to determine the number of plates that you need to get this flow rate on the column. Okay? So we have the liquid flow into the reboiler and the vapor flow from the reboiler. So basically we will follow the procedure that you have in here. And the procedure, if we look at it, the first thing that we will need to do is to plot the feed and top product composition as a point, XF and YD. So if we look at this, the XF is basically the composition at the feed, okay? The composition at the feed is 40% benzene, right? If we are feeding 40% benzene in the liquid, then from the equilibrium curve, the TXY diagram, we get this amount of mole fraction in the vapor. So therefore we can plot this value, right? Now, for the bottom product, we basically want 0.02 of benzene, and then we have 0.4 on the vapor, so we have this value as well. Okay, so we have a value for the reboiler and for the feed, and using these two values we can draw geometrically a straight line, and that's basically, we want to get from this feed that we have in the distillation column up to this part in the reboiler. Okay, so we want to go down from 0.4 benzene in the reboiler to 0.02 benzene to take out that. So basically throughout the distillation column, the mixture, if you look at the mixture will be fed at the top, and we'll need to go through a mass transfer, a heat and mass transfer, to achieve this composition at the exit. So something must occur during the distillation column to bring the feed from here to there. So this is why this is called the operating line, because that's what we need to happen in the distillation column. Right? Is that clear?
To have the liquid column.
Yes. Okay? So we basically, first of all, construct this diagram. We have already constructed it as I showed previously, right? So here the data points are not shown. We just see the diagram. From the TXY, we get this mole fraction of vapor and mole fraction of benzene. And then we locate what is the feed that is coming into the distillation column, which will be the feed point, and what is the fraction that I want in this case in the reboiler in the liquid product, which is this is the fraction. So I need to go from here to here. I draw a line, and that's my operating line. So plot the bottom product composition. We have plotted the bottom product composition. Join them with a straight line. That's it. The straight line is called the operating line and gives the composition of the liquid and vapor stream throughout the column. It is straight line because we're using the McCabe-Thiele model. Okay, so that's the model we're using, and therefore we're using a straight line. Now, what we're going to do is that the liquid vapor mixing on each stage within the column is represented by steps drawn on the XY diagram between the operating line and the equilibrium curve. So, throughout this operating line, we will have several stages by which we will have the heat and mass transfer occurring, and those are expressed as vertical lines and horizontal lines. Okay, so this is really a geometric approximation because we will need to take the ruler, and therefore draw vertical lines which will represent the change in vapor composition as it flows through a stage. And horizontal line represents the change in liquid compositions as it flows through a stage. The number of steps is equal to the number of stages required for the separation. So we will start in the initial operation, and we'll basically draw vertical lines up to the XY diagram, and then an horizontal line. Another vertical line, horizontal line. And we'll go through the whole stages like that, up to the point where we achieve the basically fit composition. You can do the same from here to there. So you can start here, draw a horizontal line, vertical line, horizontal line, vertical line. Okay? And each one will represent the number of stages. So after that, we will just count 1, 2, 3, 4, 5, 6, 7, 8. Okay? So we have 8 horizontal lines. So therefore, this column will require 8 stages to achieve that composition. Okay? And in practice, well, the number of stages is not 100% efficiency. So if you had a column efficiency, you will get the number of stages over the efficiency, and that will increase a little bit the amount of stages that you need in the column.
If the triangle is not closed, does that mean that it's like a 0.3, 0.5 plate?
If it's not closed, then you'll put it up or down. Depends.
The efficiency will probably account for it.
I think that I will, as an engineer, will always go up. Just to be sure. Normally, the efficiency will just bring it a little bit further up. So leave it like that, and after the efficiency, just close it to the top that you get. Okay. So that's the way that we calculate the number of plates manually. And that's another example where you are given the XY diagram already, and you have to calculate the number of plates for this. So calculate molar flow rates of the product, calculate the number of ideal stages. Okay, so molar flow rate will be through a mass balance that we have seen already how to do it, and the number of stages through the Thiele method, which is taking this plot and therefore calculated the number of stages. Right? So as far as distillation column concerns, that's what we're going to learn. And now what I'm going to do is go through the simulation. Okay, so we'll take a 5 minutes break, and then after this I'll open HYSYS. And I mean, I did it again. I don't know what happened on Friday. Something, I mean, always with these things, but I did it again on the weekend and it converged. Or I'm going to try it now. I don't know what is going to happen. Hopefully it will converge, okay? Anyway, we'll take 5 minutes break, and then I'll show you we'll do the HYSYS again together.
I just thought I could. You'll see international and English students. Then it's obviously like far bigger. I think like first year was obviously that were more than like it's best just to go through the unit because they have a local contracts. I've got your first year. 10 and you don't know you'd rather go from unit, it's easier, like you said, it's cost. Just a lot.
With the course, you said about because obviously there's the question saying calculate the work in the expander. There's no expander.
The work on expander?
No, yeah, because it says on the front about an expander there's a valve.
Oh, perhaps you got a.
Because
Perhaps you got another version.
Because the one on my one is a
Let me see. No, but definitely there's no
there's no
expander on this
expander, yeah,
one, so you don't need to calculate the work.
So
the
do
work
I treat
because
the valve? Because the
it's a valve,
the
yes.
pressure and the temperature changes in the valve.
Yeah, so
So
it is like
I
a
treat it
valve.
as a valve.
As a valve, so
Right,
it
okay,
is as
yeah.
a valve, and you don't need to calculate this question. You need to obtain that question.
Is it been an updated version?
I think there is an updated version in the
Is it on Blackboard? 'Cause I'd look at
Blackboard.
it,
Yes. Let me, I'm here in Blackboard.
Which you see for
Yeah, so
Yeah.
I've got an old one.
Yes.
And then can you scroll down to the process flow diagram?
Yeah,
Valves,
so-
just calculate the work in the valve.
Yes.
Cheers. You know, like, is the cluster of this building the only one with it on? Or is it on
No, you can go through RAS.
My computer
And your you don't have RAS.
I've got it, but my computer just runs so slowly. It doesn't work properly.
So any cluster computer that you can go to RAS and you can work through
So I
RAS.
work with it.
Yes, but then it's better to use the cluster because then you go directly to the software, and RAS sometimes has some problems. So yes,
Can I access that cluster even though I'm
yes, yes. I think your smartphone should open that cluster. Yes.
Okay. Cheers.
Right. So, where do you want to start from? Should we do the distillation column again? Don't tell me that. That was the problem last time. Okay. We'll see what happens, right? Okay, so you'll need to take notes So you can later on simulate that by yourself. What happened? Where is my... What happened? Right, so we have just finished the valve, and we'll go to the separator. Okay, it's not allowing me to. In the separator, we basically need only to define the streams, and that's it. That's the only thing that is needed there. Oh no. I'm not sure. Who has open HYSYS here? Nobody?
In the last year, same, I'm getting like this error when I open.
Yes. You get like too many applications open.
Yeah, the license is not complete. Yeah, it closes.
Well, the thing is that I think they have a certain number of licenses. Why is not opening? Okay, so we go into the separator, okay, and we'll define vapor outlet number A. So I'm basically just writing up the stream flow numbers, right? So this is where the vapor will go, and that's the liquid, right? So after that, I click F4 if I lose the palette, and then I will go into columns, and I select what it's called in HYSYS reboil absorber column, but basically it has one reboiler and no condensation part, which is what we want, right? So what is going to be the top stage inlet is going to be the 7, the liquid fraction going out of the separator. The overhead vapor outlet, let's call this 8, and the what? What did you say? Should be 9. Why? Okay, let's call it 9, and then 10, the bottom's liquid outlet, right? However, do we have a liquid outlet in this distillation column? No, we don't. So therefore, the bottom's liquid outlet is going to be 0, effectively. So we need to define a stream that is the vapor that we're going to take out from the reboiler. So let's call that 11. Okay? So this will be a vapor fraction, and that will be retrieved from the reboiler, okay? So the reboiler, we won't take out the liquid, as is shown here. We will take out the vapor, and therefore this is the reason why we need to specify an additional stream here. Why we don't have here that... Okay. We don't have any other inlet stream, just the top stage inlet. The column name, let's leave it like that, and that's it. Number of plates, we said that we were going to start with 5, but once you do the theoretical calculation, then you'll be able to input something that is closer to that. So let's click next, okay? Once we click next, we don't do anything else. We want once through a regular HYSYS reboiler, right? So we click next here, and here we need to specify the pressure. So this is 101.3 kilopascal. Reboiler pressure is the same, and pressure drop 0. Okay, so we're not taking into account any pressure drop through the system. So we continue next. Do we have temperatures estimates for these ones? We don't have that information, so therefore we take next. Boil-up ratio, we don't have any boil-up ratio, so we could click on next. Huh? Okay? Is that all right? Reboiler energy stream, we said that we were going to connect it to the reboiler duty before. All right? So then we go to monitor. And then in monitor, we'll have to check the degrees of freedom. The degrees of freedom for the model to converge has to be 0. At the moment, we have overspecified the system. So we take out one of them, okay? This has come to 0, but actually we don't have this rate, so we take out this one. So now we need one variable to specify, because we have a degrees of freedom of 1, so the model won't converge. So I'm going to add a spec. And what are we going to add? We're going to add the component fraction, because we have the fraction of propane going out of the reboiler, so therefore we can specify that, okay? So, component fraction, target type, stream. You need to click here, stream. So which stream we are going to take out? What is the stream that is going out from the reboiler? 10? Is it 11?
11 or 10? It's from the reboiler.
Remember that it's not the liquid fraction, it's the vapor. So it's 10?
No, 11.
11? Okay? Which component we're going to define, ethane or propane? So we can define propane in here. And we are going to define the mass fraction because that's what we have in the assignment. So what is the mass fraction that we have of propane after the reboiler? 0.995, right? Because we have 0.5% mass ethane. We click enter and we close. And that's it, it has converged. Right? So we can check that here and it's green. Normally here it will show green if it has converged, yellow if something, an inconsistency has happened, and if you get yellow then check your degrees of freedom. Or in my case, I don't know what happened to the program on Friday. It started to play a little bit funny, so sometimes if things went completely wrong, delete everything and start up to the point where things were converging. Okay? So that's it. We only need to specify the component fraction and then the system has converged. Close. Right, so after the distillation column, we have 11 and 12, right? So let's check. 11 composition, 0.992 propane, okay, which is close to 0.995 that we wanted. 12, double click, check composition, 0.76 of ethane, which is close to 0.75 of ethane that we wanted, right? So now we need to join the vapor where we have ethane coming from the separator to the distillation column. So we said that to do that we simply use a mixer. I think the mixer is very easy. You just need to define the flows. So what goes in the mixer? So the inlets, we have 8 and 12, right? 8 and 12, where we have basically the ethane going. And then the outlet, we'll need to define the outlet, so we'll define as 13. Okay? And then it converges. So then we have the ethane and we have the propane fractions here, right? So the only thing that is missing is the pre-cooler, which in this case will be heating these flows, right? It will be cooling down the inlet flow, but it will be heating the outlet flows, right? So I need to link these 13 and 11 with this pre-cooler, right? So what I'm going to do first is I'm going to define the function that is happening in each one of these flows. So I'm going to leave them separate because if I mix them, then there's no point of everything that we've done so far. So we'll leave them separate and we'll define a heater in each one because that's the function that is happening. So
I think this is for this string it's cooling it for the 13 and 11.
13 and 11 is heating up. What is cooling is the feed. So here we define a cooler because it's cooling up the feed. If it's cooling up the feed, it's heating up the outlet. It's a heat transfer.
But with high temperature, how it can cool the pre-cooler down?
Because the temperatures in here are, I mean, this is a gas phase process, so really it's a high temperature, but the feed is a little bit higher than that temperature. Okay? So the feed comes at an even higher temperature than this one. So basically, what we're going to do is we are going to join. So the inlet in here will be 13, and the outlet in here will be 14, okay? And then let's join the other. Inlet 11 and outlet 15. Now it hasn't converged because normally in heat exchangers I need to define the duty, and by that I mean the heat flow or the temperature, and I haven't defined any of them, but I have the duty from here. So the heat flow in here is 2.82 kilojoules per hour, well, exponential to the 6 kilojoules per hour. So initially what I'm going to do is I'm going just to define these two divided in two parts, or just give a number. So even I'm going to give an energy here of 50. On non-delta P, is there a change in pressure in the heat exchanger? No, we're not defining a change in pressure, okay? So, okay, so, over here. What is the number that I gave? Heat 107. I'm just going to. I think I need to label it. I'm just labeling it. Q 106. That's just a random label that I'm giving. You can give any name that you wish. Okay. So I need to click what is the inlet flow, the outlet flow, and give a name to that. It could be energy 1. Whatever you want to call it. I'm calling it Q106 in this case. And then I'm just defining a duty, which is very small in this case, okay? But it's within the range. It doesn't matter. Just define a duty for the fact of converging it right now. Those were all my trials. Okay? So this has converged, but obviously I know that this is not correct. Now, I have to do the same in here. So, which number, a name I gave? 106. So Q dash 107. Or no delta P. I need to define if there is any pressure drop. There's no pressure drop. And then the next thing will be to define the duty. I'm not going to define the duty. Should I define the duty? I think the duty will be defined later on. So I'll leave it like that right now. Well, let's define the duty. 50. Okay, it converges. So both have converged so far, but I know that the duties are not all right. So now I need to correct the duty because that's not fine. So what is the assignment telling us? The assignment is telling us that the temperature of 14 and 15, will they be the same or different? They must be the same, right? So right now the temperature of 14 is minus 68 and 15 minus 42 degrees Celsius, so they are not the same. We need to make them the same. So to make them the same, I'm going to use this Cn parenthesis A, which is the set function. And I'm going to set for these two flows to be the same. Okay? So therefore I'm going to select variable 14, and then here I select the temperature select. So I want the temperature of the stream 14 to be the same than the stream 15. Okay, right. Now they have say an inconsistency error has happened because you have over-specified this problem. You cannot define the heat flux and tell us which temperature it is. I mean, you're telling me that you need to use this heat flux and achieve this temperature, and it's impossible. We need to be able to change the heat flux. Okay, so I take out the heat flux of this stream, at least of one of the streams. Now, check, because as soon as something happens, the system will go automatically on hold. It won't be active anymore. Okay, so as soon as you have an inconsistency error, then it stops the simulation immediately because it cannot run basically with the error that you have put. So let's see if I have deleted that, if this now works. So I'm going to click on active. And then that's it. Okay, everything is blue and everything is happy. So now the temperature of this is minus 42.33 degrees Celsius, and the temperature of that flow is minus 42.3 degrees Celsius. What has happened is that I've taken out this heat flux, so the operation has been able to change that heat flux to meet the temperature of the other one. That heat flux is still defined to 50, okay? So as long as you are able to change one, then they play with this one, with that heat exchanger to meet the temperature that you can on the other one, okay? So now I've met the condition that both temperatures are the same, but I still have the problem that this heat flux plus this heat flux has to be the same as the pre-cooler. And those, if you add them up, they're not the same so far, okay? So this is 50, and this is 2.76 times to the 5. So that won't add to 1.86 times to the 6, I think. So I need to set up this system so that these two are the same heat flux as the heat flux used in the pre-cooler to link them up. So how I'm going to link them up? What I'll basically do is I'm going to use a spreadsheet, and I'm going to add the function as if I were in Excel, that this E100 and E101 heat flux need to add up to the pre-cooler heat flux and need to be equal to the pre-cooler heat flux. And to do that, I'll use a spreadsheet, more or less like an Excel spreadsheet, to make this equation. So then I input a spreadsheet. Now, when you do that, when you input the spreadsheet and you do this adjustment, click on hold, put everything on hold, because we're going to do several changes, and if we continue keeping it active, it's very likely that you'll have something the simulation won't like your changes as you do them, and then it will cause you problems. So put everything on hold, do all the changes, and then once you have finished, then click on active. And you can do that for all the unit operations. While you're doing the unit operation, you can click on hold. Once you have finished putting everything in the unit operation, click active, and then it will run. Otherwise, the system is running as soon as it can. As soon as it can, it's waiting. Okay, yeah, now I can run, now I can run. And therefore, if you make a mistake, you may run it incorrectly, causing the system to fail, and then you have the same problem that I had on Friday, that things were not happening very well. So go to the spreadsheet. Now, in the spreadsheet, I need to add the variables that I want to work with. Okay? So the variables that I want to work is E. Oh my God, which E it is? E100, E101. So E100, and then within E100, what I want to change, where is it? BB duty. It should be as heat flow, but I'm not sure why it shows as UT here. Well, I'll write UT. And E101 UT. Okay? So now I have defined the duty of E100 and E101. Where is the spreadsheet? Here is the spreadsheet. So right now what I have said is put in cell A1 the duty of E100 and write down in cell A2 the duty of 101. So did you remember that I specified 50? And this was calculated, right? So it's basically doing that. So I can change that to B1 if I want. B1 and B2. And then it appears in B1 and B2. So I'm just adding some labels. And then that's the sum. So here I want to B3 to be the sum of B1 plus B2. Right?
Because they're in lower case. They're in lower case.
I don't think it shouldn't affect. Perhaps because I have it on hold, so it's not running anything. Okay, so I'll leave it like that. Let's see if I click on active. Okay, so that's an energy variable. I'll put it on hold again. So therefore cell B3 is B1 plus B2. That's the result. And that's the energy. The parameters that I'm estimating is B3, and the connections that I did is the duty of each one of those, right? So I've input the formula that I want, and I've defined a new variable which is B3 basically. Then I close this Excel spreadsheet, right? So now I'm going to use another icon to make the adjustment. And that's basically called adjust. So is this, how do you call this tool? The spanner, yes. So you'll adjust with the spanner the whole system. Right, so what I'm going to adjust? What I'm going to adjust is basically the temperature at the outlet, right? So temperature of 14 and 15 are the same because of this set. Now I'm going to change the heat flow of these two values by changing the temperature at the outlet, right? So the temperature is what can be changed. We don't have a defined temperature, and we need to find out the temperature that makes the system converge. So I'm going to double click on adjust. So I can select either the temperature of 14 or 15 because they are the same. So I'm going to select the variable and then string 14. I click temperature, select. So I'm going to adjust the temperature. I'm going to change the temperature. Why do I want to change? What will be the target variable, or what I should change it to meet what? So now I'm going to the Excel spreadsheet and I'm going to select B3, which is the variable that I have selected. Okay. So what do I want B3 to converge? I'm going to supply this value. So what value should we supply here? 2.86 exponential 6. Oh, you have good memory. So so that's the value that I want to connect. to check, okay? Now that's it. I've done it in here, and now I'll go to parameters. And here in parameters, you don't need to change anything. It's just the number of iterations. So how many times it's going to run the program in order to get that value. So normally the setup says 10, but you can change it to 1000 to give it enough iteration if it's needed to get that value, okay? So once you have that, then I'll click active and hopefully it will. Now everybody cross their fingers. Oh no. Oh yes, I know what happened. Now, close it, okay? Now, something has happened in here, and that's that I'm specifying this heat flux, actually. So I'm over-specifying the system. So now I need to delete the heat flux that I just guessed, basically, and just invented. Right? So now I don't have this heat flux, and I don't have that heat flux. And I have these parameters, so then I click active. And it should run, but it doesn't. So let's see. I'm going to take out this adjust. Q. And then I click on so which feed is it? Which 14, right? So we click 14 and we're going to adjust the temperature by changing spreadsheet TT. Specify 2 points. .82 2.82 exponential to the 6, and then parameters 1000. Okay. Spreadsheet. I think that is Q what we need to specify. That was, yes. Perhaps that's the issue. Because Q is the heat flux. Shouldn't matter, but click on adjust. Select variables. Which one is it? 40? Temperature. Select variables. Spreadsheet. What did we say? 2 points? 82. 1,000. Okay. Or no maximum. No, it goes to or no maximum. Yes?
You've got to put like a min and a max in.
No, you don't need to actually for this.
Start value.
I think that it's a little bit sensible actually.
Let's submit without prices.
I'm giving you the solution, you just need to reply it.
It takes a lot of time. Just the calculations.
So that's it. Basically, you click on adjust. Oh, great.
Oh no.
By default,
The exam is approaching. Let's do it without ISIS. Six exams. Guys, someone say yes, yes. Say no, 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 no. Yeah. Because it's going to be the same. Yeah.
Right? So once you set that, you have the spreadsheet here. So basically Q1, Q06, Q07 heat flux. And then we have the sum of the two of them here. We click on adjust, change 12 by changing the temperature. The target variable is the spreadsheet and B3. And here, well, that's not completely correct, but specify that. 1, 2 you said, or? Okay. So you specify the number of iterations 10,000. Perhaps it was too low, the number of iterations. And then that's it. So let's have a look at it. Composition ethane 0.81.2. So 0.8.2. Composition of this one 0.992, 0.007. So is that all right? No, is that all right with the composition of the that was called in the assignment? So in the assignment it said that the ethane should be 0.75, right? And we're actually having it a little bit higher, 0.80. So what does that mean? That we're separating more than actually what we needed. So basically, what can we do? What could we do? Reduce the number of plates, perhaps, right? So who knows? I mean, perhaps having 4 will hit better 0.75, or perhaps not. So you'll need to try it.
So we need to adjust the number of plates again in the
Yes.
or it's
Reduce the number of
again.
plates. Let's say if I change this to 4. And then no, it hasn't achieved the separation. I think you need to
Can you
take
change
out.
number of plates? When something like that happens, what you do is you close down and then you open again the same file. I don't think that you can change manually number of plates. There's some
It's not as straightforward as that because we have an adjust, we have a tool, so you'll need to basically delete that, change the number of plates and run everything again. But I think that if you achieve that with the 5, I mean, don't try to optimize or anything. There's no reason to optimize. If you get that and you do a good comparison between one and the other, that should be enough. Now, another thing is that, so how do you check the final and get these plots in here? So I got these charts.
yes. Where did you get this chart?
Yeah, so you go to custom flow sheet modified, and you add a stream label. Oh no, it's not stream label. You click here, work table, and select what do you want. If you want the materials, composition, or energy streams. And it will immediately show you the table. So this is the material stream. Let's say if I delete all of those, I go into here and I select material streams and I get all the material streams. So then with that I can see how the mass flow is changing throughout the whole system. If I want to know how the composition is changing, I click in composition and I get the table for compositions. Okay. So here I have in stream 13, 0.992 and 12.80.2. And then that's it. You can discuss from that what you found out. So what I would suggest is for you this week, perhaps you can work on your model, and then next Monday, if you have questions that this didn't happen, we can go again through your problems that you have. Okay? So basically we have finished now. We've given you all the information that you need to prepare for the exam. I've uploaded the past exam papers, which are quite a lot. So now, if you finish the tutorial, there's more fun. Now with the exam papers, And basically what we intend to do on the next Monday, we'll still meet here at 9, and we'll go through any problems you have with the simulation, and we'll go through the exam papers, okay, as well. And that will be, yes?
Just think questions coming from tutorials, or
Yes, you can bring questions from tutorials, and then we'll look at the solutions and see where you have problems and everything. Okay, on Monday. So basically that will be 2 hours for you. So I'll spend some time this week on this module, and then next Monday perhaps you can clarify anything that you have, and then you can continue your revision and submission of the assignment by yourself. Okay? See you.
No, the question, by asking this question.
I'm not too sure how do we find because for pre-cooler 2, after we come out, we're supposed to get a vapor liquid composition, right? It seems like Hysis is indicating that. How do we find the composition, the vapor and liquid percentage? We're thinking about it. I think we've been discussing about ourselves. We're not sure how we obtain that.
The vapor liquid composition. You have the temperature that you have.
You should guess.
Here.
Yeah.
So if you go to the equilibrium,
No, we don't know the temperature. Basically, all we have is we have the input temperature, we have the
You
work
should
done.
guess.
or you can get the temperature, right?
Guess temperature.
We have to guess temperature, then we know.
From the equation, delta H. So you do the integral from T1 to T2.
No, but can we use delta H in that sense?
So normally here you need to get the temperature here.
Yes.
You need this temperature from
Right.
this heat flux.
Yes.
And with the temperature, you go into your curve,
Yeah.
equilibrium curve, and then you get the vapor and liquid
But
composition.
this one, you will come in, you can use the latent heat of vaporization, right? Because you have at 217, you already reach the dew point of the curve.
Okay,
Yeah.
so you're on the gas phase,
Yes.
but you're still cooling down.
Basically, cooling from the dew point into the liquid vapor composition. So basically, the delta T for gas is 0, right? From the gas phase. But now you have to consider delta HV. But how do, because delta HV here is given as an equation. As this. So how do we solve this?
Like some questions.
So delta HV.
Yes, because delta HV, I mean, in the work examples that you see, this is a fixed value. So we can solve for
Exam, no.
but we don't have. In this case,
Maybe somebody
what
else
is
needs
the
to speak, someone with a clearer voice.
what is the equation we use to do that?
That will be the temperature at which you
don't realize how
start
difficult that is.
having the vaporization occurring.
So there will be 217 Kelvin. So if we substitute in, then
And
we
then this will be 217.
So what's the question?
so basically if we use 217 here,
That was
then we,
what I asked.
then we can find out what it is.
Are you incapable of asking yourself? Do you not have a clearer voice?
here
Do you not have a voice?
you have-
Are you incapable of
So
speaking?
which phase is the system
It
at
don't
this
bother me
point?
that much.
This
I
point
just
is
did this for 3 years.
Yeah? But once we cross the pre-cooler 2,
I
you
don't
get
get
a
You got
it.
vapor liquid, so you need to know the fraction of vapor liquid that you have.
Using the temperature from this heat flux, right?
what temperature.
Yes, you need to get this temperature from the heat. You have the heat flux.
Yes, we have the heat
So
flux.
that will be the delta H, that will be Q, and then you get T.
CPT to minus T1.
Okay. But I'm sure that way it doesn't work.
I don't know if it works, I'm just thinking too.
No, because
Yes, because if you apply a Q delta H that does the complete conversion, then that will be delta H total to get from one to the other. But since you have Q, you will get in the middle, and that will be
okay,
Q.
wait, I'm just thinking here because okay. So if
So
by that
delta
logic,
H will be
delta H will be equals to m.
Yes,
this
that's
times
what-
m dot.
yes.
But in this case, you must find what is t, right?
yes,
So you have to solve this equation
yes,
with this z. to the power of Z up here.
Yes, I think you'll need
How do we do
Excel.
that?
Solve it in
okay.
Excel.
You should guess every temperature.
Yeah, the iteration.
Yes.
Okay.
It's a lot.
So you can't do it
Only
like
the Excel.
annually.
No, that will be very hard to do manually.
Okay. So it's not manual calculation without some formula.
You don't need to do everything manual. I mean, you need to show the formulas that you're using and the input values, but in this case, you just solve it in Excel. I think some of your colleagues are solving everything in Excel, not manually, but you still need to show in the report the
But can we
equation.
show we solve manually, for example, and then give the temperature, final temperature, that's it. Or we need to show how we solve it manually. What
You
do we
need to show the equations that you used,
Yeah.
basically to solve it, and the result that you got. So I should be able to understand what were the equations that you used and how you cannot say, and I used this and then I got that like that. So you need a little bit development. Yeah, so that's
Wait.
Assumption.
Then for the submission of this report, like, what do you want us to extract from HYSYS? Is there like a print function or print a report from HYSYS?
yes, you can print
Final
the,
table, it's enough.
you can print the model,
Okay.
but basically the composition table that you get.
Okay.
So the composition table that you get, that will be
So the
that
model,
will be
the
enough,
full
and then
idea.
you'll just
the answer,
explain.
comparing the
You just
answers.
explain. Yes, you just
Why your
compare.
manual calculations versus the HYSYS?
I think that the key importance of the HYSYS will be the explanation of what were the differences, the discrepancies, where did they come from,
Number of
what was your
stations.
experience, and all this, so that I can really show that you've done it, basically.
Excuse me, he has questions.
Yeah, so about the exam question, we have 5 questions.
Can you just briefly explain 5 questions and how many questions
Yes.
are you going to ask from your part, from Miguel's part?
Yeah, so there's going to be 5 sections. 5 sections.
5
and you
sections
need
or 5 questions?
5 sections.
Wow.
5 sections.
Each one question.
And you need to select 3 sections out of 5 sections. From these 3 sections, there are a number of questions.
Shit.
So how many from your...
Sub-questions.
From your part or from Miguel's part?
How
From
many
both-
sections will
both.
you?
No, I mean,
From the 5
many
questions, how many sections is there?
For this part, 3 questions.
Okay.
And for Nigel's part, 2
sections.
sections. Yes.
so we can choose 2 questions from Linus and 1 question from you, yeah? For example.
Yes, if you want to.
Just like
It's
Yes,
choice.
if you feel-
Yeah, yeah.
It's a choice, so you can. I think it will be good if you contact Nigel as well to ask
And
him
it can
if
be
you have
good if
any
I choose not to
questions.
answer Nigel's question.
Yes, so
I
it
love
will be-
calculation. I don't have time to be cramming memories.
Is it calculation from Nigel's question or just...
No,
No.
Nigel, because you didn't do any
didn't do
calculations with him,
calculations.
so there's all theory from his side, because that's what you discuss with him, isn't it? So what you have learned is what you'll be asking.
Yeah, it's possible.
So you can ask whatever you want on the sections once you get them.
I have a question regarding the last part of your lecture about this one. So you mentioned that from the example to plot this. So this is for the P condition, and this one for the top. So from this, so for this example, so for the feed is 6% of methanol, and the top is 96. But when I plot this here, 0.6 and 96 is out of this region. How can I?
No. It's just because this is methanol, ethanol, right? And this is plotted for methanol. Methanol. So how much methanol do you have? 60% methanol.
Can you do a HYSYS and share with everyone?
Top of 96.
Okay, methanol, 60% methanol. So you have methanol, 60%, right? But you don't know
But by the way, the answer is going to be the
how
same.
much you will
Everyone's
have in
answer, I mean, the
equilibrium
HYSYS.
in the vapor. So you are taking
think it's
methanol,
gonna be the same.
ethanol, but remember that this
If
is not
do it in a
methanol,
proper
ethanol.
way.
This is methanol, liquid vapor.
Saving everything. What you are saying here?
I don't understand what you mean, but in here the both axis is for the benzene, for same material.
Yes.
This is the same.
Yes, so this is 0.6.
0.6
Yes, 0.6 of methanol in liquid.
2013 далеко, могу ближний какой-нибудь взять.
We actually need the DXY.
the lecture.
Or just last year.
Okay.
Methanol, ethanol.
Are you going to smoke?
Because this is 40% in the liquid phase, and that would be 56% in the vapor phase.
This degrees
56%
40%,
Yeah, all about
in
that.
the liquid phase. 56% in the vapor phase, so that would be
Biz labga qarayapmiz, aka. Eksperiment o'tkazmoq. O'z spesimenlarini.
This is my last
in this case you get 6.
So,
Not done.
from her part, is it enough only to learn from the
In the
tutorial
liquid.
questions?
No, you have to
That
study.
would be in the liquid phase.
To Nigel.
In this case, you didn't have
Nigel?
distillation column on the top.
Neville.
You didn't have a distillation column on the top.
You mean the reflux?
Yes, so this was a vapor phase,
He's
right?
absent.
Or in this case, you have you have a refluxation, so you have a distillation column. So this is not the vapor phase,
Не
that's the
трогай,
liquid
пожалуйста.
phase.
In this case, how can I calculate stage? Because I
So
cannot float.
you have 0.6
Let me see.
methanol, and then methanol in the vapor,
And we don't know.
Big head.
the reflux ratio will be 4.
Me small head.
57.
96%.
57.
Percent of the methanol.
60.
I think you need the curve of the TXY for methanol ethanol.
hair.
So you know how much, when you have 96% methanol, how much do you have in the vapor phase. So you can actually obtain the vapor phase.
А, мен сразу после эксперимента
This 96 is in liquid phase, you mean?
Yes, that's the
Вот
liquid.
ертең барайын деватырмын, барасың.
Because you have a condenser.
Қазір бастайтын шығармын, соны қарай деватырмын, қалай бастайды. Өз спесимендерін салды ғой.
You have a reflux ratio in this case, so it's not the same as this one. Because in this one you didn't have a condenser.
Yes.
In this you have a condenser.
Жоқ, мен саған хабарласып жүр дегенде ол баяғыда айтып жүрген.
But I understand that too. So when we have reflux, so the top product is mainly about the vapor, and then reflux means the reflux liquid into the distillation. So how can I understand this one is liquid? Because mainstream for the top reflux, the stream is vapor. Should be
No,
vapor.
no, 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 no. Depending on the type of distillation column. Yes, this doesn't specify which type of distillation column it is. But in this case, you have here this type of distillation column, right?
So that's what
But
you
in
are.
this case, here you can guess that there is a condensation because you have a reflux ratio.
Did you get what I mean?
Yeah, but I understand
I
about
had
the,
that question in
what I
mind as
understand
well.
generally, but because of the what the gravity and then density difference, the top product should be
You should see
mainly
the
about
closest
vapor.
one. Not the fire, which is
No.
10 years ago.
Normally the top product is liquid. In a distillation column, it depends. You can take out liquids out of one side or liquids out of the bottom. Or you can take vapor, liquid. It will depend on the operation of the distillation column. There's no fixed value. There's
So
no
anyway-
fixed stream.
So anyway, in this case, because I don't have TXY curve for methanol and ethanol, I cannot put this
Yes.
one.